Trebuchet Project. Problem definition. In a group of 4, we were to design and build a functioning trebuchet out of materials that we requested or that were already provided. The overall goal of the trebuchet was to launch a 21-gram marble with maximum efficiency. Some part of the trebuchet was to be designed and fabricated from 3D printer or laser printer, whereas the rest was made from materials supplied to us. The only major restriction was that the entirety of the trebuchet had to fit into a 12-inch by 12-inch box or be assembled and functioning within 2 minutes. Potential energy, kinetic energy, and efficiency. The simulation trebuchet had similar numbers to the measurements of the actual trebuchet. The kinetic energy of the virtual trebuchet equaled out to be approximately 4.725 joules. The potential energy equaled out to be approximately 9.48 joules. Within the measurements and calculations that the simulation came up with, the energy efficiency of the virtual trebuchet equaled 0.782, while the range efficiency equaled 0.609. The overall range of the virtual trebuchet equaled 124.233.
Design process. Shown here is the A-frame design which we ultimately used for building our trebuchet. Design, the long arm was 10.5 inches long and the short arm was 4 inches, overall 14.5 inches, which pivoted at a height of 10 inches. The sling used to fire the projectile was 11 inches long, and the counterweight's mass was 6 pounds. Our group considered an A-frame design from the very beginning of planning for its stability and relative ease to fabricate, construct, and use. In designing the specific lengths, heights, masses, and other values, we used trial and error of the simulation to perfect our trebuchet. Minor tweaking of values in this simulation allowed us to find an optimal range and efficiency for firing the projectile. A useful aspect of our design was the employment of bearings to smoothly rotate the arm. We used the heavy counterweight, planning to result in a long throw.
Problems during testing. The box would scrape the ground, not allowing for full rotation of the arm. As well, the weight distribution of the counterweight wasn't very good and caused a non-smooth swing of the arm. The box also wouldn't stabilize, so in effect, it moved the arm around the pivot so the trebuchet couldn't keep a very straight path. Issues with release mechanism. We had problems creating a good size release pouch, and we didn't use enough string to attach the pouch. So instead of flinging a projectile forward, it would swing straight up and fall right back down where the trebuchet was placed. We also didn't allow for a long enough release mechanism, slipping, so it would slip off sooner and sometimes shoot backwards or also contribute to shooting straight up. What worked well? The arm was able to move quickly because we had bearings into the sides of the structures, which caused it to move smoothly and not get stuck. And it could have added to the range if we ever got it to go forward. The side structures were built very sturdily. Even though the box was huge and kind of unstable, the structure remained solid and structurally sturdy. What didn't work so well? The base we built, while sturdy, wasn't tall enough for the box to clear the ground. The box was too big and unstable. We went more for looks than it working. We need to come up with a better way to secure the box. And we had to raise the bearings because of the new base that was added at the end.